I would like to turn now to my friend and colleague Dan Mote, President of the NAE, to offer his welcoming remark and perspectives on the workshop. I was asked to get a brief bio to introduce him. I received as a brief one about 3 pages, single-spaced. So I will just a couple of remarks. For, I will tell you what I like in his vita. First, he's a mechanical engineer. I'm a mechanical engineer. I like that. He spent quite a bit of time at Berkeley, and was a very distinguished professor at Berkeley, and also become vice chancellor at Berkeley. And I like that too, although being a graduate of Stanford, maybe that's not perfect. Then he became the president of the University of Maryland in College Park, and was president for 12 years. And if you look at the accomplishments of the university during that time, it is quite outstanding. And I know I was a president of Caltech overlapping with his tenure at Maryland, and I can tell you how respected he was and still is in a community, in a country. In addition to all that, he has been extremely active for many years in professional societies, including the NAE. And NAE has served in many different positions, and recently, as you know, agreed to come here as the president. He has received many awards, and I will only mention only one, and it's likely not the most important by far in terms of extremely distinguished, but the one that I find extremely interesting. And he was the Distinguished Teaching Award recipient at the University of California, Berkeley. And receiving a teaching award in any university, I think, is quite an accomplishment, especially Berkeley. So Dan?
Well, thank you very much. I didn't expect you were going to read my resume so carefully. Even my mother, I don't think, has ever done that. But I very much appreciate the introduction, but especially Jean-Loup, you and Rod's leadership of this group. It's extremely important study group. And I feel very privileged, actually, to have this opportunity to come and just say a few words about what I've been thinking about on this topic. And I haven't participated in the group, so I warned the committee already that I'm not intentionally trampling on anybody's toes, even though I say things that may be provocative or maybe already been dismissed by the committee. So be it. Humor me. I'm an old guy. Basically. I just really want to add my welcome and thank you to all of you who are coming to this and the effort you're putting into this, and all of you out in cyberspace also that are involved in this, because this is a very important topic, and everyone should engage in this, not only during this workshop, but also in this topic. And really the sharing your experiences, expertise, and perspectives on these educational and career pathways of engineering talent, and how we should think and talk about engineering careers, and how we teach engineering and employ and mentor and develop engineering talent, and how we characterize the dynamics of the market. This is really a time for great questions, and I think the only thing reassuring about this is everybody on the planet has the same problem, that this is not a unique problem to the United States. So the questions around engineering talent are really a lot more complex than they might first appear. And I think, we started on this many years ago, actually, and the problems still are around. The questions actually haven't been answered. And so I'd like to offer a couple of perspectives on this engineering and engineering talent question that I've been thinking about, and try to understand why this is such a big problem. Why is this a big headache? How can it take so long? You can go to the moon a lot faster than you can answer this question. So the first question, I think, to look at very briefly, now I'm not going to go on and on about this, is what is engineering? So basically, engineering creates solutions to problems of people in society. That's what engineering does. In the short form, engineering solves problems. This is really the essence of engineering. The challenge to engineering is creating solutions that work. That's what engineering does. And what I mean by work, it satisfies all the constraints required to do that. The second question is, what comprises the substance of engineering? Well, the substance of engineering is everything required to create solutions that work. That is the know and the know-how. The no derives from familiar topics, right? It's everything. Sometimes people say it's applied science, but that's not even close to correct. That's a subset of the no. There's certainly a science, experience, experiments, workforce, talent, needs, tasks, constraints. All that falls into the kind of no category. Then there's a know-how part. It derives from vision, creativity, experience, judgment, leadership, organizations, finances, workforce, risk management, models, guesswork, tests. All of that is in the know-how part. And the know-how and the know come together, and they essentially provide these engineering solutions. Now, if we think just for a moment, how did we get here? That is, how are we in this state? The first kind of organized engineering field was military engineering. And that was the Roman legions were pretty good at this. And then when the Roman legions were not doing their legion thing, in order to keep them together, they had to give them something to do. So they had them do civilian projects. The Roman legions built roads, aqueducts, bridges, walls, all this kind of stuff. Big civilian projects. And from that derived civil engineering, basically infrastructure problems, big infrastructure problems. So then at about the middle 19th century, we had the Industrial Revolution arrived. Steam engines, so we had power other than manpower and horsepower, and also machines. So the civilian engineering or civil engineering wasn't quite suited properly for that. The know and the know-how didn't come through that slice. You needed to create mechanical engineering, so to build machines and to operate machines and to keep steam boilers from blowing up and all kinds of things that are necessary to operate this in this phase. So mechanical engineering came in to get the know and the know-how into that slice. Then, of course, about 1890 or so, late 19th century, electricity came on the scene. Lights and electric motors, AC, DC, transmission lines, power generation, that whole electrical domain, big, important electrical domain. So we needed know and know-how for that. So create a new field of engineering, electrical engineering, and automotive engineering, and aero engineering, and nuclear engineering, and so on. So every engineering field derived, was essentially formed to get the know and know-how to execute some tasks that are necessary for the community in these fields. That's basically how engineering was put together. So you can see in this process right away you're leaving out an awful lot of engineering at each step, because in fact the problems of people in society don't necessarily fall under the umbrellas of these concentrations, which are very important concentrations, by the way, but they don't cover everything. So when we speak of engineering talent, we have to think of this picture that not everything that's important in engineering falls into under these umbrellas, which ultimately we tend to use as if they are the holy grail of how we define engineering under these tents of various kinds. But in fact, not everything even comes close to fitting under these tents. So when we speak of talent, of course, we are addressing the talent required for engineering, and of course, I was very happy to hear Jean-Luc talk about the fact that the committee has already decided we're really talking about talent for engineering. We're not talking about talent for engineers for engineering. Because a lot of people who do this work, in fact, in this domain, don't call themselves engineers, are not engineers. In fact, I very much believe that this field of engineering, in fact, is very clearly identified. I gave you what I think it is. However, the people in engineering are not clearly identified. They're all self-identified. I'm an engineer because I say so. I have no card that says I can call myself a mechanical engineer and I can say someone else is not a mechanical engineer. There's no way to do that. I'm self-identified. In fact, a lot of people identify themselves as scientist, engineer, inventor, entrepreneur, innovator. They'll just decide which one of those they are. So self-identification essentially characterizes people in terms of how they look at that. So why is this distinction important? So why am I making a big deal out of this? Well, it's important because many people do engineering, even at a very high level, who have never earned an engineering degree, don't describe themselves as engineers, and may not even have any degree at all, as a matter of fact. In fact, the National Academy of Engineering has over 25% of its members have no engineering degrees at all. In fact, we have 6 officers of the Academy, 3 of them have no engineering degrees at all. Okay? And of course, we have people with no degrees. You know, I mean, you name a few. You know, Bill Gates and so forth. Dean Kamen. I mean, you know, they're not hard to find. So the reason is simple, and it's important to this question that the reason is they are elected to the National Academy of Engineering not by what they call themselves, not by what they've studied, by what they have done. What they have done. And this is the part that seems to get lost a little bit in this discussion about talent and engineering and the educational process. So it's really important to do this. And by the way, this whole thing doesn't just fall on it's not just engineering that we're talking about. It's also a lot of others. Take, for example, the Large Hadron Collider, this big scientific instrument in Asia, in Europe, that essentially, you know, identified the Higgs boson. You know, multi-billion-dollar project, 3,000 physicists working on this thing. It was a tremendous project, one of the great engineering projects of this century. Very difficult, very expensive, huge headache. The whole thing is an engineering project, start to finish. Everything about that's engineering. But it's got 3,000 physicists work on it. So these guys are doing engineering work. But if you ask them, their interest is not actually engineering. They're looking for the Higgs boson. They want to get some fundamental matter understood, as they should, by the way. But the fact of the matter is they're doing engineering, too. So do we account for them in our classification of engineering talent? My gosh, they're doing something that's spectacular. Is that talent? Is that engineering talent? Leave that question for you. Take NASA's Curiosity, the Mars rover. Mars, okay, take that thing off, get it to Mars, get it in orbit, get it down on the spectacular landing process, and then get it to work the first time. Can you imagine? The first time that complicated thing worked? It's unbelievable. You can't get an electric toothbrush to work the first time. So the whole thing is engineering, start to finish. Of course, if you go to the NASA website, you won't see engineering on there, by the way. That's another problem we've got. But nonetheless, the people who worked on that thing were doing spectacular engineering. Probably the most significant, in my view, engineering achievement of this century so far is that Curiosity dropping itself on Mars and working. The only time NASA mentioned it as engineering, by the way, is when there was a blackout for a couple of days on the communications. You remember that? The engineers are going to solve their problem. That's what NASA said. So NASA for 60 years has had scientific achievements and engineering failures. It's just been consistent. But that's a problem for us, another problem for us. But once again, it gets back to this talent question and what is engineering, who's doing engineering, and how do you tally the people who are doing really important engineering? That's the problem I have. So many basically have demonstrated these talents and these contributions that do not fit into the classifications that we normally use to identify contributions to engineering, which is basically where you got your degree and what in, and what is the job classification you're in. What is the title of your job classification? Those people, those physicists and those guys at NASA, they would not fit into engineering job classifications and so forth. So this is the problem we've got in this discussion, okay, on how we characterize talent. We need a better understanding of the dimensions of engineering talent, really based on my view, the key thing is on engineering undertaken rather than relying solely on classification of graduation statistics and job classification as guidance. Because we know more about, in fact, these educational history, and we know more about the job titles, we tend to use those for degreed engineers, because that's the data that's available to us. So the data essentially gives us a stilted view of people who are really doing engineering that's in fact quite spectacular, as a matter of fact. So I think maybe our conclusions ought to be careful about these exclusions. And even maybe we should think about if we can get some good idea how to make them inclusions. That's the question I kind of threw out on the table. I don't have the answer to that, but I think it's a topic worth some attention. So, of course, we also know, by the way, that the pathways to career advancement for many engineering graduates is through management tasks or tracks or leadership and so forth. Often it follows a graduate degree in management or MBA or even in engineering. About 60% of BS graduates in engineering, we go back to the ones we identify as graduates of engineering, they go into technical work, as you might expect, in engineering computer science. This percentage drops down after a decade to about 40% because they move up into leadership roles. Well, leadership's a big part of engineering. It doesn't strike me that's necessarily a bad outcome. And then, of course, as you get to be an old-timer and you're age 50 or so forth, you do more and more management things. Like John Liu and me, you run big things, right? So you're doing engineering. You're engineering the Saudi empire. But so that's a natural course. I don't see that as the problem, actually. I think that's just the way it is. I think it's the missing, that we're missing, our job classifications are missing people who do great engineering. And of course, there are a lot of work I have read about that look at the effects and the way we educate students and advise them on their occupational opportunities and really foster their agility and continuing learning and development that affect their career pathways. So there are things we do that affect their career pathways, and those are, of course, will be something that the committee is going to do, I'm sure, quite well, and it's very important. And we're just beginning to understand the influence of students' decisions to pursue degrees in engineering and engineering graduates' decisions to seek employment in engineering that are based on other experiences they have, like how their experiences from the demographics and various mentorship they've got. And this mentorship is really an important issue all the way along. I would say understanding these influences of mentorship and their university experiences and how it affects their outcomes could be an important issue for this whole domain. Now, the market for engineering talent is really complex, and I would say that everybody on the planet that I know of is looking for engineering talent. I've never been to a place that wasn't looking for engineering talent. The Chinese are looking for engineering talent. The Singaporeans are looking for engineering talent. The Taiwanese are looking for talent. Japanese are looking for talent. South Koreans are looking for talent. U.S. looking for everybody on the planet. In UAE, they're looking for talent. Everybody is after this question. So everybody's got the same problem. And the U.S., they're looking to the U.S. actually to help solve this problem. So I think that's why this committee's work is going to be so critical. It's really what you call the proverbial hot topic. Now, recently we've had a surge in enrollments in engineering. And in fact, over the past decades, the undergraduate enrollments increased by 40% overall, about 24% at the MS level, and even 71% at the PhD level over a decade, which is very heartwarming in effect. I don't know how long it's going to last exactly, but nonetheless, it's significant change. The last NSF data I had on this is fewer than 5% of the undergraduate degrees in the United States are given to engineers, fewer than 5%. All right, 4.5, 4.4%, last I saw. That is, I don't know if you have a sense of where that puts us down, but the world average is about 13.5% for our countries. And in this group are countries that we don't normally consider, while they're very fine places, we don't normally consider them as competitive in the technological world with us. Places like Cameroon, Burundi, maybe Saudi Arabia, may be in there somewhere. I don't know. So in a very small number. So we're really undersupplied with graduates in engineering, especially since half of them don't continue in engineering and half of them go into other directions. So this also makes me ask this question. Maybe it's these other fields of people who are going into engineering, as they have for a couple of millennia, that actually is making up the difference on this. So I think that's this question's got to be resolved. Where does all the talent come from that we have currently? Accelerating change that we're seeing in the country is creating a big problem here. We all know and we all agree we have accelerating change in our society and technological changes. That means things go up faster, they come in faster and they go up faster. Nokia, you know, was the world's largest cell phone company for a couple of decades. 3 years, dead, out of business, gone, disappeared. They missed it. They missed the turn. They missed the turn. They thought the cell phone was a communication device, not a personal assistant, and they didn't get there in time. History. Apple comes in. Now Apple is having some real competition with Samsung, same kind of pattern. So in this environment we have, where things go up really fast and go down really fast, it creates havoc for engineering education and the workforce. That means you can be very popular and very much in demand, and when you're in demand, you are in demand, and you be like petroleum engineering, and you get 110 or 120,000 a year starting salaries for a BS level, because everybody wants a petroleum engineer. But then when you go out of demand, boy, you really do go out of demand, and you get into a situation where you're really not valued. That is, your field is dropped. That's happening faster than ever currently. That's a problem for the workforce. Some comments by the committee on this question. How should U.S. universities, I mean, my own perception is U.S. universities have to solve this problem. It's not going to come through the for-profit education or through just online education. I think U.S. universities have to come back into this picture of a responsibility to re-educate the workforce on a regular basis because of this accelerating change. If that doesn't happen, why would anybody enter the profession to start with? I mean, it has to be an attractive process by which one can get qualified in a field, have an experience. When that field goes away, which is going to, you're not going to have things going on forever here. They need to have a chance to retool and change directions. Auxiliary education at universities now is no longer getting tuned up in your own field the way it used to be, getting the latest gizmos in your field. It's now going to be going into a new direction where the action is. The NAE had a study called energy future. The energy future. What is it? Oh gosh, 2009 study on America's energy future. This was a big study to tell the country about what was coming in energy, so policymakers would know where all the value proposition is in energy for a country, nuclear, fossil fuels, and so forth. That study did not mention, and by the way, it's a very expensive study with very high-level people, very skilled, the greatest experts you could find on this topic, and we're very proud of it. We raised a lot of money for it, put it out, and we just were really puffing up over this study. It missed entirely fracking, hydraulic fracking. Hydraulic fracking is not mentioned in that study. Within 2 years, all of a sudden, the thing is making the United States energy independent wasn't even mentioned, didn't even get a byline. In fact, the only thing it said about gas in there was, there's a lot of it down there, but you can't get it. Therefore, it's not going to make a difference. So this is just exemplary of the accelerating change and how fast things can turn and how that can change the workforce picture entirely. And that's part of the challenge of this committee, is how to deal with this reality, because this is the reality. Well, maybe I should stop at this point. I've talked already too long. I really want to thank the committee for taking on this project. You can see this is really a big project, and there's a lot of meat to this project that's really fundamental to the prosperity of the country, and other countries too. Other countries will be watching this because everybody's facing the same problem, basically. So you should really consider this one of the most important studies the Academy has and probably maybe ever has, because it's really hitting the core fundamental issue about how we're going to essentially develop our future technologically and how engineering is going to play into it. So thank you very much for your work, and I really look forward to helping you any way I can and keeping track of where it goes from here. Thanks very much.